The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. When I say happy morning, I know you all are happy. So today's class, we are going to see a happiness quote by Dale Carnegie, and it goes like this. Happiness does not depend on the external conditions, but it is governed by our mental attitude. Yes, children, our mental attitude decides the happiness. Instead, we are searching for it everywhere. So I would like to share a message which I was browsing through today morning. It goes like this. Our body secretes 4 hormones which are important for happiness. They are endorphin, dopamine, serotonin and oxytocin. Now these are secreted by the activities that we do. The first one, endorphin, is being secreted by the physical activities we do. When we do physical activities, our body gets rejuvenated. You feel so happy. That's why we love our PT periods the most in our school timetable. The next one is dopamine, which is being secreted by the small tasks that we do in our daily life. So keep doing your work sincerely. You will find happiness in whatever you are doing it. The next one, serotonin, is being created when we do something that benefits others. That is, when you help others in small things, definitely you will find happiness in that. And the last one is oxytocin, where you would experience this in the film Munna by MBBS, where you can see hugging is the best medicine that gives happiness. So when you hug your friends or your relatives or your parents, definitely that will secrete this hormone and you will get the happiness. So these 4 hormones play a very important role in creating happiness within yourself. So children, I want you all to do these activities to make yourself happy and also to make others happy. Today's class we are going to start with Ellingham diagram. The last class we were seeing about concentration of ore, metallurgy process, where we were learning about how removing impurities from the ore by 4 methods: hydraulic washing, froth flotation, leaching, magnetic separation. You remember? So then we were also seeing about calcination and roasting and using the reductive, that is reducing agents. But today we are going to see, as we know there are more reducing agents, it is not that easy to select. We have already discussed about coke, carbon monoxide and electricity as the best reducing agent. But there is always a confusion which reducing agent we are supposed to use for which metal. But we know highly reactive metals we use electricity. But still there are some methods to find out the best reducing agent. So that's how this Ellingham diagram was elucidated, where we are going to learn how to find out the best reducing agent. If you see, thermodynamics has given us an equation where for standard conditions, Gibbs free energy del G naught is equal to del H naught minus T del S naught, where we know this is Gibbs free energy, this is enthalpy and this is entropy. And we know del G, that is Gibbs free energy, will help us to find out the spontaneity of a reaction. How we will find out? We know there can be 3 values for del G. If del G value is 0, we know the system is in equilibrium. There is nothing happening. The system remains constant at equilibrium. If the value of del G naught is greater than 0, that is being positive, it is non-spontaneous, which means the reaction will not occur on its own. What happens if del G naught is less than 0? It is a negative value, which means it is a spontaneous reaction. It happens on its own. So by concluding with thermodynamics, what happened with the scientists, what they decided, something that is related with temperature plays an important role in Gibbs free energy. So for that, they did a graphical representation between del G and temperature, Gibbs free energy and temperature, to find out the best reducing agent. So this diagram was called as Ellingham diagram. So in Ellingham diagram, we draw a graph between Gibbs free energy and temperature for various reactions and find out which is the best reducing agent by determining the value of del G at various temperature. So by drawing the graph, we will be able to find out the best reducing agent that can be used in the process of metallurgy. So now you should be very careful, because I will be giving you 2-3 examples to find out the best reducing agent by comparing the graphs. So children, now we will see an example of Ellingham diagram. We know during reduction process what happens, any metal will undergo oxidation, that is will be treated with oxygen to form metal oxide. Now this metal oxide only has to be reduced. If it has to be reduced, we need to find out which is the best reducing agent. Now consider this Ellingham diagram, which is between the Gibbs free energy and temperature. Now you can see in the center a straight line which shows del G is at equilibrium. Now there is a point here which I have marked where it gives rise to T1 temperature. So at this point del G is equal to 0, that is the reaction is remaining constant, and I have marked here two portions, part A and part B. When I say part A, del G is less than 0, that is this is my 0. So this portion will be the value of Gibbs free energy which is negative, that is less than 0. So when I say the B part, now this line, the dotted lines you can see is the line for this equation, metal plus oxygen giving metal oxide. So here the part A is del G value less than 0, because this is T1 temperature, where I can say this portion is before 0, that is negative, and the B part is greater than 0, which shows del G is positive. This is all for the reaction 1. This dotted line is for this reaction 1, and part A shows the value of del G less than 0, and part B, that is this portion which is after 0, more than 0, shows the value of del G greater than 0. Now how are we going to find out whether this reaction is spontaneous at what time interval? So for that, when you consider this A part, I am going to consider only my A part. Before T1, this is my T1, you can see the dotted lines. So before T1 what happens? Metal is combining with oxygen to form metal oxide. Am I right, children? So at this point of time, A part, I know the value of del G is negative, that is it is less than 0, that is it is negative. So at T1, at this temperature T1, del G is equal to 0, because it is a point of intersection. Del G value is 0, which means it is at equilibrium, but before T1 the value of del G is negative. For which reaction? Metal, when it combines with oxygen, it is forming metal oxide. So A part is negative, which shows this reaction is spontaneous. What is spontaneous? It happens on its own. Now when you consider the reverse reaction, because in thermodynamics we used to consider the reverse conditions. What happens to all the values when you reverse the conditions? Whichever were negative will become positive, the positives will turn into a negative value. So when I am going to consider the reverse reaction of this, that is M plus O2 giving MO. When you consider the reverse reaction, MO gives M plus O2. So what happens here? In this case, the del G value which was negative will turn positive because it's my reverse reaction. So when it becomes positive, the reaction will also turn to be non-spontaneous. I hope you are able to follow, children. Once you consider the reaction, when you reverse the reaction, the conditions also get reversed. So the value of del G which was negative became positive. So the spontaneous reaction became non-spontaneous reaction. Now this is what we studied about A part. Now let us consider the B part. This is my B portion, that is, this is my B portion, right? Now I know my B part is del G value is greater than 0. See, this is my 0. Del G value is 0 at equilibrium. So this portion will be greater than 0. So del G will be positive. So M plus O2 MO, del G is positive, which is a non-spontaneous reaction. Now if I am going to reverse in my B part, what happens? MO giving M plus O2, the del G positive value will become negative and the reaction will be spontaneous. I hope you are able to understand the Ellingham diagram. Please understand very carefully, children. Value of del G, if it is a constant line, the value of del G is marked with a point of intersection. So the portion before that 0 is always negative and the portion after that 0 is always positive. So considering this dotted line for this equation, M plus O2 giving MO, this will be negative, this will be positive. So the forward reaction of A part is spontaneous and the reverse reaction of B part is spontaneous. I hope you are able to understand. I will give you a few more examples with 2-3 different metal oxides so that you understand much better. Okay, children. So children, now we will take an example where what is the use of using a reducing agent is what we are going to learn. See, when you consider this graph between Gibbs free energy and temperature, we have T1, T2, T3 are 3 different temperature at which this Ellingham diagram is being drawn for 3 metal oxides. We have silver oxide, we have mercuric oxide and zinc oxide. So let us consider the reaction where silver oxide will be forming silver metal with the liberation of oxygen gas. Mercuric oxide again mercury metal and oxygen gas, zinc oxide with zinc metal and oxygen gas. If you see the graph, from the graph we can very well understand that for silver and mercury, the temperature is at a low scale, that is T1, T2 are at low temperature. That is, these two reactions are taking place at low temperature. But what happens in the case of zinc? For zinc, it definitely requires a very high temperature compared to the other 2 metal oxides. So certain metal oxides which do not require high temperature, that is which can even take place at low temperature, those do not require a reducing agent. If you see the same metal oxide, when we use coke as a reducing agent, instead of heating, we can take zinc and carbon monoxide. Otherwise, when it takes a very high temperature, definitely the process becomes very expensive. You need to spend a lot to get a refined zinc metal. So to avoid all those, we started finding out the best reducing agent that can be used for the metal oxides which needs really very high temperature. So for that purpose, we are going to learn about Ellingham diagram with reducing agents which can be used for which metal oxides. So you all are with me, children. Now the next diagram is going to help us or teach us how to find out the best reducing agent from a list of reducing agents. So here is a graph of 3 reducing agents which we are going to see here. Carbon monoxide getting converted into carbon dioxide, carbon getting converted into carbon dioxide and carbon getting converted to carbon monoxide. Children, understand the graph very carefully. The graph is drawn between Gibbs free energy and temperature. you can see three different lines. One line in the center which I have marked as B part. One line goes from bottom to the top which I have marked as C part, and one line comes from the top to the bottom which I have marked as A part. So for A, del G you can see it is coming down, for B it is just a straight line, and for C it just goes upward. So this is the graph. The graph was given to you. Now we need to find out which is the best reducing agent. So how are we going to do it? Let us consider one line at a time. Now if I am going to consider my A part, what is my A part? C getting converted to CO, that is carbon monoxide. What happens actually in the reaction? Carbon solid combines with half oxygen gaseous state and get converted to carbon monoxide again in the gaseous form. So we know to find out del N, that is to find out the number of moles of a reaction, it is number of moles on the product minus number of moles on the reactants. Difference between number of moles of products and reactants will give us the value for del N. And we also know for solid it is always considered 0, we do not consider that. So now NP minus NR, in the product side it is only 1 mole, and in the reactant side solid I do not consider. So we will take only half oxygen, so that is half. 1 minus half will be half left, which is positive. So there is an additional increase of half a mole in the value of del N. So when number of moles increases, del S actually increases. The randomness actually increases. That is, it becomes more positive. Entropy increases, it becomes more positive, and we know in thermodynamics del G is equal to del H minus D del S at standard condition. When del S is positive, the value of T del S becomes more negative. So when it becomes more negative, what will happen to our Gibbs free energy? It also becomes negative. So when del G becomes negative, A part, which is our A part? This is our A part, the line which comes down from the top to bottom, the graph where you can see Gibbs free energy falling down, decreases because it is reaching a negative value. That shows that this graph is spontaneous. Carbon getting converted to carbon monoxide is a spontaneous reaction. Now let us consider the B part. Which is our B part? The center line is our B part. So consider the reaction, carbon getting converted to carbon dioxide. Carbon solid combines with oxygen to form carbon dioxide. Again calculate the value for del N G, NP minus NR, 1 minus 1, 1 in carbon dioxide and 1 oxygen. So 1 minus 1 becomes 0. So when the value of del N becomes 0, there is no change. No change in entropy also becomes 0. So when del S becomes 0, what will happen to our Gibbs free energy? That also becomes 0, which means this is the line that we get that shows there is no change in Gibbs free energy. So the reaction has got a state of equilibrium. It is neither spontaneous nor non-spontaneous, it is equilibrium. So now we will take the third graph, which is carbon monoxide getting converted to carbon dioxide. So when you take the C graph, carbon monoxide combines with half oxygen to give carbon dioxide. Here you should be careful, children, all the reactants or all the reactants and products are in the gaseous state. There is no solid state. So when I am calculating my del Ng, it will be 1 minus 1 plus half, which is 1.5. So 1 minus 1.5 will be half. So there is a minus half, which is a decrease in the number of moles. So that shows a decrease in the entropy. When there is an increase in temperature, increase in entropy, decrease in temperature, decrease in entropy. So when del S becomes negative, from thermodynamics, T del S, negative into negative will make T del S positive. So that will make our del G also positive. So when del G becomes positive, you get a graph for C part. which is a non-spontaneous reaction. So from these three, A, B and C, now we know which reducing agent we should take. Which one, children? Yes, we will take the A part, that is I will consider coke as a best reducing agent that will form carbon monoxide, which is a spontaneous reaction. I hope you are able to understand this Ellingham diagram. We will see one more example and I will give you a trick to find out the best reducing agent. Okay. So if you consider this diagram where you can see again A, B and C part is being drawn, but with one metal oxide, that is zinc oxide, because we were discussing for zinc oxide to get reduced we need to find out the best reducing agent, right. So when you say T1, T2, T3 are T different temperatures at which these reactions of A, B and C takes place. Now assume I cannot take C getting converted to CO2 because I know that in that del G value is 0. So I have only two options, either this A part or I should consider this C part. So I have to find out which will be the best reducing agent. So I know zinc oxide, when it combines with carbon monoxide, it gets reduced to zinc metal and carbon dioxide. The agent, that is the reducing agent, will reduce the metal oxide and itself will undergo oxidation. We already know that the oxidizing agent will undergo reduction and the reducing agent will always undergo oxidation. So again here zinc oxide, when it combines with carbon, it forms zinc and carbon monoxide. Now the question arises where I should use which one as a reducing agent. Either I should use carbon monoxide or carbon. Now this is a trick that we need to follow. The metal oxide placed higher in the diagram, this is the metal oxide which is placed higher in the diagram, can be reduced by the element involved in the formation of oxide lower in the diagram, where whichever the del G graph forms down, which forms a lower area in the graph, that will be considered as a best reducing agent. If you see, this is my graph for zinc oxide. So I have two lines, one line, second line, third line. So this line actually lies below zinc oxide. This is my third line, it lies below zinc oxide. So I will be considering the A part, which is a second trick. You should give priority for temperature where del G is negative. That is at low temperature where del G is negative. See, if you see, this is the point of intersection where this is my zinc oxide line and this A part line is joined at a temperature T1, which is the lowest temperature compared to T2 and T3. So always give priority for the graph or for the line where the low temperature is considered. So del G is also a negative value. So if you consider this graph, T1 is at low temperature, which is my A part. So that is referring to coke. So I will consider the second equation as a best reducing agent. I hope you are able to follow this, children, because you have been given a diagram in page number 155. Do not get confused. When you take portion by portion, you will be able to understand. If I draw the whole graph, you will get into confusion. That's why I made it into small graphs for better understanding. Ellingham diagram is important because it is helping us to find out the best reducing agent. If you see, children, iron extraction, you know, we have been studying from our 10th standard. A blast furnace is there where a hot of blast air is being blown from the bottom. You put a mixture of limestone, coke and hematite ore, that is iron ore. What happens actually there, you know, the coke will combine with the oxygen that is being sent from the bottom and forms carbon dioxide. Later the carbon dioxide will form carbon monoxide, which will be used as a reducing agent in the whole furnace. We know Fe2O3 will combine with carbon monoxide to get itself reduced to iron metal. And also we know that iron metal will contain some impurities which can be removed by the decomposition of limestone. Calcium carbonate will be decomposed to form calcium oxide and carbon dioxide, where calcium oxide is used as a flux. Calcium oxide will combine with silicon dioxide to form calcium silicate. You remember all these equations which is already given in the textbook in page 156. There also we've learned that we don't get the pure iron. We'll be getting cast iron, we'll be getting pig iron, and we'll be getting wrought iron. So you have to just learn all those, how one by one, each point of pig iron, wrought iron and cast iron. And also when you consider the extraction of copper, in copper also same thing happens. We consider coke as a reducing agent. Copper 2 oxide or copper 2 sulfide will be combining with coke to form copper 2 oxide, right? That's how the reducing agent will be reducing the metal oxide to the metal. So there, that is also important, extraction of copper. Just go through, I'll be posting the video for you to understand better. And then you have 3 reactions given in page 157. See, this can come in 1 mark question. FeS plus 3O2 giving FeO plus SO2. Again considering silicon dioxide, similarly with copper. Okay. Extraction of zinc from zinc oxide can be done with direct heating with coke, where you get zinc and carbon monoxide. With that, this Ellingham diagram is getting over. When you consider the electrochemical principles of metallurgy, we'll be learning about aluminium extraction. In aluminium extraction, we have learnt in 10th standard that cryolite and alumina is mixed together because the melting point of alumina is very, very high. So the whole process will be stopped if you are not using cryolite. What is the function of cryolite? Cryolite is used to reduce the melting point of alumina, thereby increasing the electrical conductivity. And we also know that carbon lining is used, graphite rods are used. We know always the metal get deposited at cathode, right? They get reduced and deposited, and the anode mud will be separated. And there the graphite rods have to be replaced then and there, otherwise that will combine with the oxygen and form carbon dioxide. This is all what we have learnt, right? Hall-Heroult process. I will be posting the video for better understanding, because this we have already learnt in 10th. You just have to give a small reading to that to understand much better. Okay. Now let us get into a refining process. Refining, we have hardly 5-6 methods which we have already learnt. So let's go one by one.
Thermodynamic principles of metallurgy. Almost all metals are found in the combined state as compounds on the crust of the earth. In order to extract a metal from its compound, the combined form is first converted into a metal oxide, which is then reduced to obtain the free metal. While some metals reduce easily at low temperatures, others get reduced with difficulty even at very high temperatures. Is it possible to predict the most appropriate reducing agent and the optimal temperature for the reduction? Let us find out. Thermodynamics play a very important role in metallurgy. It helps to predict the feasibility of metallurgical transformations. One of the simplest yet most important concepts is that of Gibbs energy. A negative delta G represents a spontaneous reaction, and a positive delta G represents a non-spontaneous reaction. The equation delta G is equal to delta H minus T delta S calculates the value of delta G for a reaction from the values of delta H, the change in enthalpy, and delta S, the change in entropy for the system. The change in Gibbs energy at a particular temperature can also be understood in terms of equilibrium constant K. Under standard conditions, the free energy change for a reaction is directly proportional to the negative of the natural log of the equilibrium constant K. The more negative the free energy change, that is, the more spontaneous the reaction, the larger is the equilibrium constant at a constant temperature. Based on the above equation, the requirements for a spontaneous reaction to proceed are: the energy change must be negative, the equilibrium constant must be positive. Let us see how the above requirements can be met. The energy change will be negative only if the enthalpy change is negative and the entropy change is positive. This happens when the temperature is high. This increases the value of T delta S, making Gibbs free energy more negative. Thus, the reaction becomes feasible. By plotting a graph between Gibbs energy and temperature for the formation of metal oxides, the feasibility of the reactions can be predicted. This graphical representation was first used by H.J.T. Ellingham. It is therefore known as the Ellingham diagram. Thus, the conditions under which a metal oxide can be reduced to its metal can be gauged from this diagram. Let us see the significant features of the Ellingham diagram. Consider a metal M which reacts with oxygen to form its oxide. This reaction can be written in terms of Gibbs free energy. We plot this value on the graph. As the metal is a solid, in this reaction, the entropy decreases and thus delta S is negative. As the temperature increases, T delta S becomes more and more negative. Consequently, delta G becomes less and less negative. This is seen clearly in the graph. The graph shows that all the plotted lines have an upward slope and delta G becomes less and less negative with increasing temperatures. This is the first significant feature of the Ellingham diagram. The second significant feature of the Ellingham diagram is that all the plotted lines are straight lines. An exception to this is when the material melts or vaporizes. With the rise in temperature, a point is reached when delta G versus the temperature graph crosses the zero mark of delta G. All oxides which have their Gibbs energy below this line are stable, while all oxides above this line would be unstable. Thus, we can see from the graph that oxides of metals like silver and mercury are unstable and hence can be decomposed to get their respective metals. Lines of some reducing agents such as carbon and carbon monoxide are also plotted in this diagram. This helps to interpret whether the given reducing agents are useful or not. The Ellingham diagrams made for sulfides and halides suggest how difficult it is to reduce sulfides and halides. Let us recapitulate what we have learned in this module.
Before getting into refining, there is a topic with oxidation and reduction. What does it mean? See, we were discussing only in metallurgy about reduction process happening, but there are elements or compounds which also undergoes oxidation simultaneously. Because we know this redox reaction is a spontaneous process which happens in every chemical reaction that we have seen. So there are few examples given as of they are important, like extraction of gold and silver using this oxidation process. So I will be giving you extra notes for those which are in exam point of view that are considered important. Now we will get into the last topic, which is refining. Refining is a process of getting the pure metal by few methods. So we have liquation, distillation, electrolytic refining. Distillation, we have learnt again, there is a difference in the boiling point. So the metal is being heated at a temperature where the low boiling point vaporizes first, will be collected separately, condenses, and you get the metal. Liquation is a process where low melting point metals are heated in a slope. So what happens, the metal which has got a low melting point will melt first and will be collected in its purest form. Electrolytic refining, we know that's a process where we consider the same metal and electrolytes, anode and cathode, oxidation reduction take place simultaneously, and the best example we have learnt is copper itself undergoing oxidation and also undergoing reduction. You just have to do a small recap of what we have learnt in 10th standard. So now we will get back into the other methods where zone refining. Zone means a particular area where impurities are soluble in its melted form, that is in its molten state, than considering the solid state. That is, when I heat a metal, it starts melting, the impurities will be soluble in that and you can remove it separately. Now how does this process happens? There is a zone where you put the metal and a mobile heater is being moved from left to right continuously. The moment it is being moving, the metal part which is getting heated up will start melting, and when that process happens, the metal will crystallize out, leaving the impurity there. So at one particular time, all the impurities get concentrated at one particular portion and you can collect the metal separately. This has been widely used where there is an application of semiconductor. That is, if you want the semiconductors to be refined, we use zone refining method. The next one is vapor phase refining. See, vapor phase refining, from the name it is clear that the metals are being converted into its volatile compound, and that volatile compound will be decomposed back into a purest metal form. So there are two conditions important for that. First, the metal which we select for this method should be forming a volatile compound, and the same volatile compound should be easily decomposable. Unless and until it is easily decomposable, we will not be getting the pure metal. There are two processes involved in that. The first process is a Mont process where, example, nickel, when it combines with a carbonyl compound CO, it's not carbon monoxide, children, it is carbonyl compound, you get nickel tetracarbonyl. Now that nickel tetracarbonyl will be decomposed to get the pure nickel. The next method is Van Arkel method, where it is mainly used to remove oxygen and nitrogen impurities. So once these impurities are removed, the metal will be in its purest form. Example, you can see zirconium, when it combines with iodine, it forms zirconium tetraiodide, which again decomposes to get the pure zirconium metal. So these are the two important processes, and Mont process always comes in the exam, that is for your board exam. So consider all these reactions as important for you. The last method is chromatography, which we have learnt already, children. You have column chromatography, where you have the compound which has to be separated out, dipped in a solvent, and the mobile phase will be there and there will be a stationary phase. Once you put the solvent, the impurities will be separated out and only the metal will be remained separately. So that process we call it as chromatography. There is a chromatogram, paper chromatography, column chromatography, so many are there. So if possible, I get a video, I will also paste that. You just have to go through it with 2-3 lines which are important, like very useful for purification of the elements which are available in minute quantities, not in a big amount. Only for less amount we use this. We have paper, column, gas chromatography, pictures are also given. So that will be helping you to understand. And last page is uses. Just go through the applications where all aluminium, zinc and copper can be used, children, in our day-to-day life. So with this chapter gets over. I'll try to include the videos with the respective portions so that you can understand much better. And if you have any doubt further, please call me. And you have done your revision test very well. I forgot to tell you in the beginning. And I want you to prepare for the next 2 chapters, 3rd and 4th chapter. I may not give you problems, but I thought I'll be giving you the derivations of integrated equations and theory in both the chapters. So please learn and do your revision test well. Thank you, children. Stay home, stay safe. Thank you. Take care. Bye.
Extraction of iron. Iron is mined from the Earth's crust in its combined state as an ore. It needs to be extracted from its ore before it can be used commercially. Let us see how iron is extracted from its ore. The extraction of iron from its ore is a 3-stage process. It includes concentration, calcination, and smelting. In the concentration of ore stage, lighter impurities are removed from the ore. In the calcination stage, moisture and volatile impurities are removed from the concentrated ore. In the smelting stage, iron ore is reduced to iron. In this lab, you will be taken through the steps of iron extraction. Let us start right away. Note: iron extraction takes place at high temperatures, and hence all personnel wear protective equipment to keep safe from potential hazards. Iron is mainly extracted from its principal ore, hematite. Ore obtained from the mine contains gangue, which largely consists of silica and earthly impurities. The light earthly impurities are removed in the first stage of extraction, concentration. Let us see how this happens. First, powdered ore is added into the hydraulic classifier. Click the powdered ore to add it to the classifier. A jet of water is passed through the bottom of the reservoir. This thoroughly mixes the content. The lighter gangue particles move up and are washed away from the top. The denser particles of the ore settle at the base and are collected via an outlet. The concentrated ore still has volatile impurities in it, so it has to be processed further. It is taken for calcination, which is the second stage in the extraction process. The second stage of iron extraction takes place in a reverberatory furnace. Concentrated ore is poured onto the hearth of a reverberatory furnace. Click the concentrated ore to add it to the furnace. The burning coal present in the furnace increases the temperature inside. The ore is subjected to this high temperature in a limited supply of air. As the ore gets heated sufficiently, moisture and volatile oxides from the ore evaporate and the ore becomes porous. The resulting calcined ore is now ready for the third stage, smelting. Smelting is carried out in a blast furnace. The blast furnace is a tall structure and can be divided into zones depending on the temperature and the reactions that take place in each zone. The calcined ore collected from the reverberatory furnace is mixed with coke and limestone in the ratio 8:4:1. This mixture is called the charge. The charge is poured into the furnace from the top through the cup and cone arrangement. Click the charge to feed the furnace. A preheated blast of air is sent into the furnace from the bottom. This air is at a high pressure and at an extremely high temperature of 1500 degrees Celsius. At this temperature, coke, which acts as a fuel, burns and produces carbon dioxide in the combustion zone. The carbon dioxide formed moves up the furnace and reacts with more coke, thus getting reduced to carbon monoxide. This, being an endothermic reaction, reduces the temperature to 1200 degrees Celsius. The carbon monoxide formed in the combustion zone rises to the reduction zone at the top of the furnace. The temperature in this zone is 400 to 700 degrees Celsius. Carbon monoxide reduces the iron oxides in the ore to iron at this temperature. The iron formed at this temperature is in its solid form and is called sponge iron. The sponge iron moves down and melts in the fusion zone and slowly sinks to the bottom. This molten iron has some dissolved impurities. Meanwhile, the limestone present in the charge decomposes to give calcium oxide. Calcium oxide reacts with silica impurities in the ore to form the slag, calcium silicate, in the slag zone. This molten slag sinks to the bottom of the furnace. The molten slag, being lighter, floats over the molten iron. The slag and iron are then collected from different outlets at the bottom of the furnace. The volatile impurities form hot waste gases and are removed through an outlet at the top of the furnace. The molten iron obtained is called pig iron. It is solidified in sand molds and cast into various shapes. Most blast furnaces continue to operate continuously for 10 years once commissioned, with only periodic shutdowns for maintenance purposes. Let's quickly recapitulate the steps in the extraction of iron. The powdered ore is concentrated in a hydraulic classifier. Here, the lighter impurities from the ore are removed. Next, the concentrated ore is calcinated. This involves heating in a reverberatory furnace. The volatile impurities and moisture are removed in this process. The calcined ore is smelted in a blast furnace. During this process, iron oxide is reduced to iron. The molten iron obtained is called pig iron. It is solidified in sand molds and cast into various shapes.
Copper exists both in its native form and in combined forms. Some common ores are copper glance, copper pyrites, cuprite and malachite. The extraction of pure copper is a 5-step process. This includes concentration, roasting, smelting, Bessemerisation and refining. Click any process to learn more about it. Copper is mainly extracted from its principal ore, copper pyrites. Copper pyrites contain many siliceous impurities called gangue. To remove these, the ore is first crushed and then ground to a fine size. Being a sulfide ore, it is concentrated by the froth flotation process. The froth flotation tank contains water, to which collectors such as pine oil and stabilizers such as aniline are added. The pulverized ore is then added to this tank. A rotating paddle called the agitator mixes the contents in the tank. Compressed air is blown, in which froth is created in the mixture. The ore particles are wetted by pine oil and rise to the top in the froth. The impurities get wetted by water, become heavy and settle at the bottom. They are removed periodically through an outlet. The froth is skimmed off into a settling tank. The concentrated ore settles at the bottom. It is then removed and dried. This concentrated ore still has some volatile impurities in it. Hence, it is taken for roasting, which is the second step in the extraction process. The second step of copper extraction is called roasting. It is carried out in a reverberatory furnace. The concentrated ore is placed in the furnace. It is subjected to a high temperature with a limited supply of air. Here, the copper pyrites get oxidized to form copper-1 sulfide and iron-2 sulfide. Large amounts of sulfur, which are present as an impurity, also get oxidized to form sulfur dioxide. Copper-1 sulfide and iron-2 sulfide get further partially oxidized to form copper-1 oxide and iron-2 oxide respectively. Other impurities such as arsenic and antimony form volatile oxides. The roasted ore is now ready for the next step, smelting. Smelting is carried out in a blast furnace. The modern blast furnace is water-jacketed throughout. It is made up of steel and is lined by refractory bricks. It has outlets for waste gases at the top. A mixture of roasted ore, sand and coke is dropped into the furnace through a cup and cone arrangement. The mixture is heated strongly while hot air is simultaneously pumped in through pipes called tuyeres. The reactions that started during roasting take place here too, and oxides of iron and copper are formed. Most of the iron-2 oxide combines with silica or silicon dioxide and gets converted to form iron silicate. This is called slag. The copper-1 oxide that is formed recombines with iron-2 sulfide to form copper-1 sulfide and iron-2 oxide again. Therefore, to prevent this reaction, it is very important to remove all the iron impurities. Now, the molten material contains sulfides of copper-1 ions and iron-2 ions along with sand and coke. This is called matte. The slag and matte are removed from different outlets. The copper matte or coarse metal is now ready for the fourth step, Bessemerisation. The molten matte produced during smelting is transferred to a Bessemer converter. A blast of hot air is blown into it through the tuyeres. Once again, the remaining iron-2 sulfide gets oxidized to form iron-2 oxide. This in turn combines with sand to form slag. In this way, all the iron is removed. Copper-1 sulfide forms copper-1 oxide. Since there is no iron left, it reacts with copper-1 sulfide and forms copper. The molten mass is allowed to cool. The dissolved sulfur dioxide gas slowly escapes. This gives a blister-like appearance to the solid copper. Therefore, at this stage, it is called blister copper. The blister copper still has some impurities and has to be further refined in order to get pure copper. To purify it, the blister copper is first heated strongly in a reverberatory furnace in the presence of air. This is called poling. This copper is further purified by electrolytic refining. The electrolytic cell contains acidified copper sulfate as the electrolyte, a cathode made of a pure copper sheet, and the blister copper as the anode. Copper ions, along with impurities of iron and zinc ions, go into the solution from the anode. However, only copper ions get reduced preferentially and get collected at the cathode. The less active ions of gold and silver settle at the bottom as anode mud. Let's recapitulate the step. The finely divided ore is concentrated by froth flotation. Next, the concentrated ore is roasted. This involves heating. The roasted ore is smelted in a blast furnace. The copper matte then undergoes Bessemerisation. The blister copper is then refined by poling, followed by electrolytic refining to obtain pure copper at the cathode.